Okay, so we solved our benchmark problem, and now I want to explain to you the error analysis for this two-dimensional problem. Like before, actually for one-dimensional problem, we had two error types, right? We had the area error and we had the L2 norm error for one-dimensional problem, and you solve that. The order of convergence for linear element is 4, and for quadratic element is 8. And quadratic element is good when we have a constant charge distribution, right? Later, for one-dimensional problem, we considered a non-uniform charge distribution, and I showed that when charge distribution is not uniform, we should use higher order elements. That is true. For example, for some problems, for example, magnetostatic. When you have uniform current density distribution, in the solution region, quadratic element is enough. But when you want to do simulations like eddy current simulations that you have non-uniform current density in electromagnetic problems, you should use higher order elements to get a good result. Or you should increase number of elements if you use linear or quadratic mesh elements. So we have this error analysis for our 2D benchmark problem again. And you can see this definition for error, right? Actually, we have this definition. Definition is based on the L2 norm. Definition of error here. You can see this equation. 1 divided by NP times summation of the exact solution minus finite element solution squared, right? So how we can calculate this integral, I will explain. Here you can see the result, and H here is the mesh size. Actually, H is the same as dx and dy in our problem. So here, as you can see, when we reduce the value of H, when we reduce the mesh size, we can reduce the error here, right? And here, as you can see, when we increase the number of elements, or actually by decreasing the size of elements, which implies increasing the number of elements, the numerical error is monotonically reduced, right? So this is for linear triangular elements, but the rate of convergence is better for quadratic mesh element. But also consider this is really a hard problem, complex problem, because we have discontinuity of electric voltage here on the boundary. So how we can calculate this integral or this summation, actually the discretized form of the L2 norm integral? In the finite element method, after solving the problem, we do post-processing. And in the code, we have information about quantities of the problem solution variable only on mesh nodes. And for example, if I want to find the value of voltage for an arbitrary point inside each mesh element, I should do interpolations, right? Like one-dimensional problem. So here, suppose I want to find the value of voltage that is here for this point. First of all, I should find this triangle, and then I should map this x and y coordinate to reference coordinate. Then I can do interpolation. So for one-dimensional problem, we wrote a code directly. But for two-dimensional, I want to use this MATLAB function that we will use it frequently. You know, for this problem, we generated the mesh directly, right? We generated the mesh directly, actually a structured mesh. But I want to show you another method for generation of the mesh. Okay? Here is one method using Delanoy triangulation. Here in MATLAB, we have this function, Delanoy function, or Delanoy triangulation. As you can see here, we have x, we have these inputs, x, y, or in the case of three-dimensional problems, we have x, y, and z, right? So the output of this function is connectivity list. The output of this function is connectivity list. For example, I want to do a test. Let me create a new script and write here mesh test 1. CLC, clear, and close all. And I generate arbitrary points in my solution domain, right? Like before, we can generate actually mesh points like this. So here I copy paste and I delete connectivity list and I run this code. So here are points, right? Mesh points. I can plot like before P1 and rest, the first row, and the second row is here. So if I run this code, you can see mesh points, but we don't have connectivity list. So if I write here, connectivity list is Delanoy function P transpose, because the input of Delanoy function should be a matrix number of points times 2 or 3 for two-dimensional or three-dimensional problems. So if I run this code, you can see the connectivity list here, right? So Delanoy triangulation is a computational geometry function. And using this function, you can generate or you can triangulate arbitrary points on a plane, right? So here, if I plot the mesh, you can see the mesh. Actually, after calling this function, I should alt transpose it again. And now if I run, you can see the mesh, right? So in the previous code, we generated the mesh directly, a structured mesh, but here we used the Delanoy function. And now if you see this is good. Why we should generate a structured mesh, right? The reason is Delanoy function is used for convex domains And for non-convex domains, we should modify it. For example, this is a convex domain, but this is not a convex domain. This is a non-convex. This is convex. And this is not convex. What is the difference between convex and non-convex domain? In a convex domain, if we draw arbitrary segments, right, these segments totally belong to this domain, right? When these 2 points, initial point and the end point of this segment, exist in the solution region, so all points of this segment exist in the solution domain. So this is definition of a convex domain. But in non-convex domain, as you can see here, the initial point and the end point are in the solution region. But here we have points that are out of the solution region. So this is not a convex region. And in most of problems, we are faced with these geometries. So for example, here, if I write here mesh test 2. CLC, clear, close all. If I generate arbitrary points, so for example, I use the mesh grid function x and y, or let me use this function p is equal rand, that is a random function, 2 by 100, right? Actually, this is a random function. If I run this, you can see arbitrary points from 0 to 1, right? I used the MATLAB random function, generate 100 random points, and I have x and y coordinates. You can see these random points, right? So if I use the Delanoy function to generate mesh for these random points, you can see this mesh, right? You can see the mesh. So Delanoy function is used for triangulation of arbitrary points on plane, or for 3-dimensional problems in a 3-dimensional space. As you can see, the output of Delanoy function is a convex region, is a convex domain, right? This mesh is convex. So for non-convex domains, we should modify it. So how we can modify, right? Do you have any question about the Delanoy function?
Not in particular about the Delanoy function, but I have a question on the random function. How the points
this is a random function. If I run here rand, it gives me a random point from 0 to 1. But if I write rand 2 and 2, this is a 2 by 2 matrix, 4 points. Here I wanted to generate 100 points, 100 mesh points. So I called rand 2 by 100. So the first row is x coordinates. The second row of this matrix is y coordinates of mesh points. So if I want to generate a mesh for a non-convex region, for example, let's generate mesh for a region like this. for a region like this, L-shaped region. So here I can write a new M file and save it as mesh test3 and save. So if I copy this and paste it here, and again I can copy, paste here. So I can write P for an L-shaped region. L-shaped region. Consider this is 1, 2, 3, 1, 2, 3. So we have coordinates of corner points, right? So here I can write 0, right. This is 0, this is 1, this is 2. 0, 1, 2. So I can write 0, 2, 2, right? 1, 1, and 0. Also 0, 0, 2, 2, 1, 1. I place breakpoint here, run. You can see these corner points, right? So if I run the code, you can see the mesh here. So I have these corner points, and this triangle is axis, right? This triangle is axis. This is not the solution region. So when we want to generate the mesh for non-convex regions, we should first generate the mesh and remove extra triangles. So here you can see how I can remove extra triangles using this method. I can calculate the center point of each triangle, right? Here I write C. What is the center point of a triangle? Center point. Summation of x coordinates divided by 3, summation of y coordinates divided by 3. So I write x center is equal P 1 and connectivity list 1 and the rest, right? X coordinate of first point of all triangles plus this 2 and 3, summation of x coordinates divided by 3. What is the y coordinate? Is summation of y coordinates divided by 3. So here also I can plot this. I can plot xc and yc, x, the color red, plot, right? So you can see the center of each triangle. So now we should check which of these points are out of the solution region, right? Out of solution region. So this point, how we can detect? Again, in MATLAB, we have a good function that is called inPolygon, a computational geometry function. So the inPolygon function, we have arbitrary points on plane, and we have this polygon. We want to know which of these points are inside this polygon and which of these points are out of the polygon. So here you can see this function. xq, yq, xv, yv. Actually, xv and yv are coordinates or vertices of the polygon, and the output of this function is a logical vector, right? So I can write this in is equal in polygon xc, yc, and inside of our polygon, this is our polygon, P1 and the rest, P2 and the rest. So here you can see the output of the in polygon function. That is a logical array. 1, 1, 0, 1, 1. It means 1 point is out of the polygon, right? Consider that our polygon is counterclockwise. So now I can modify the connectivity list function. I can write here connectivity list is equal connectivity list of all rows and in. If I write this, I remove one column. So now if I run this code using index programming again, if I run this code, this is our mesh, right? So we generated mesh for a non-convex domain using Delanoy function and detecting what triangles are out of this polygon. So we have a better function than Delanoy function in MATLAB. It is not a function, it is an object. And we have a number of methods for this object that we can use. It is Delanoy triangulation instead of Delanoy function. If we use this object, we have a number of methods that we can use, more flexible. So I copy this, and here, instead of Delanoy, I write Delanoy triangulation. And if I run the code, here I write connectivity list. As you can see, the output of Delanoy triangulation is not a matrix, simply is not a matrix, is an object, right? This is Delanoy triangulation and it is an object. So we have points, connectivity list, constraints, and we have a number of functions. So here, if I write my mesh, and let me place a breakpoint here, run mesh, we have points, connectivity list, constraints. So if I write mesh dot, if I press the tab key and write points, points, I have coordinate of the points. If I write connectivity list, I have connectivity list, right? So here also I have another functions. I can write this function, circumcenter, right? For example, if I call this function, as you can see, I can have the central triangles. Or we have another good function, point location. If I input an arbitrary points, for example, point 0 and 1, this function finds the corresponding mesh element, right? So we have good methods in this object that we can use.